collisions, direct collisions, type 2, 3 spheres. In 2008, we had 3 identical smooth spheres lying on rest on a smooth horizontal table with their centres in a straight line. So the fact that they are identical is important, which means that their masses are all the same. The first sphere is given a speed of 2 meters per second and it collides directly with the second sphere. And we're told then that the second sphere then goes on to collide directly with the third sphere. And given that the coefficient of restitution for each collision is the same, it's E, then we have to find in terms of E the speed of each sphere after 2 collisions have taken place. So 2 collisions taking place would be P colliding with Q, Q colliding with, or what's their speeds after Q has collided with, or. If I'm to call the 3 spheres P, Q and or. We then have to show that there will be at least one more collision. So something's going to happen afterwards. So let's focus on the first part of the question first. We're going to draw a diagram and then draw a table showing before, mass and after. So we have 3 identical spheres, M, M and M. Just for ease of reference in the question, I'm going to call the first one P, second one Q, and the third one or. The first one has an initial velocity of 2 meters per second and is heading for Q. And then in the second collision, Q will head for or. But in the first case, both Q and or are at rest. Okay? So our table then, before, mass and after, is going to be just looking at P and Q for the first collision. So if you fill in the table, press pause on the video now. So you should have 2I for the first one, mass is M. Don't know what its velocity is after, so we're going to call it P. Second one is at rest, has the same mass, don't know its velocity after, so we'll call it Q. And again, our coefficient of restitution is E. So we're going to use our 2 equations for principle of conservation of momentum and Newton's law, experimental law of restitution, to set up our 2 simultaneous equations and then solve for the velocities after the first collision. So if we do the first one here, we have our principle of conservation of momentum. So M1U1 plus M2U2 equals M1V1 plus M2V2. So again, always making sure we sub in for our masses and then cancel afterwards, but showing your work always. Don't just go straight to the answer. So we have M times P and M times Q. Okay, so now I can see M is common all the way across, and therefore that leaves me with P plus Q equals 2. So we'll call this our first equation. If I go on to the next page then, we have our Newton's experimental law of restitution. And again, these both can be found on page 51 in our maths tables. And we have V1 minus V2 is equal to minus E times U1 minus U2. So if I'm subbing in there, I end up with P minus Q equals minus E times 2 minus 0. So in other words, P minus Q is equal to minus 2E is going to be our second equation. So I don't need to do anything to both of these equations because I can clearly see that the Q's are going to cancel straight off, which makes life easier for us. Nice handy pair of simultaneous equations. And therefore that gives us 2P is equal to 2 minus 2E. So of course if I take out the 2's as being common there, that leaves me with P is equal to 1 minus E. And now I can sub that into the first equation, or the second, doesn't matter. And then I have 1 minus E for P plus Q equals 2. So if I rearrange that to get Q on its own, I'll have 2 minus 1 plus E. So therefore Q is equal to 1 plus E. So now we have the velocities for P and Q after their first collision. So for our second table, now we're going to focus on, going back to the diagram, P has now hit Q, so Q is now going to take off with a velocity of 1 plus E, and it's going to collide then with R, which is at rest. So we're going to repeat this process all over again, making out our table for before, mass and after, principle of conservation of momentum, Newton's experimental law of restitution, simultaneous equations, and solving for their velocities after their collision. Okay, so if we again pause and fill out your table for before, mass and after for Q and for R, given that E is still the same. So we have 1 plus E and 0 for R. Their masses are the same. And again, I'll call it P and Q. If you prefer to call these different letters so you're not getting confused with the velocities of the first two, that's fine. Or some people like to call them V1, V2, V3 and V4. Again, that is perfectly fine. I just always stick with P and Q each time on my tables, making sure that I'm referring to which sphere's velocity it is. Okay, so for principle of conservation of momentum, we have M1, U1, M2, U2 is equal to M1, V1 and M2, V2. So subbing in, we have M times 1 plus E plus M times 0 is equal to M times P and M times Q. So again, now I'll only cancel across for my M's, which leaves me with P plus Q is equal to 1 plus E. So that's my first equation. And then if I do my Newton's experimental law of restitution, so V1 minus V2 equals minus E times U1 minus U2. Well, then I have P minus Q is equal to minus E, and then 1 plus E minus 0. So P minus Q is equal to minus E times 1 plus E. And again, then I want to set up my simultaneous equations. You can, of course, multiply out your brackets there. It doesn't make a difference what you do, okay? I'm just going to keep it like that because I can see I have a 1 plus E common there, which I'm going to take out, okay? So I'm going to set up my two simultaneous equations side by side then on the next page. So we have P plus Q is equal to 1 plus E. And then we have P minus Q is equal to minus E times 1 plus E. So I can see my Q's are going to cancel here. I'm not going to need to do anything to either of the equations, which gives me 2P is equal to 1 plus E minus E times 1 plus E. So if 1 plus E is common there, and I take out the 1 plus E as my highest common factor, well then I'm left with 1 minus E. And of course, if I divide across by P then, I have 1 plus E by 1 minus E, which is actually the difference of two squares. So x squared minus y squared is equal to 1 minus E by 1. Sorry, doing the y 1 minus E bit. So x squared minus y squared is equal to x plus y by x minus y, right? So we have the x plus y is going to be 1 plus E, and the x minus y there is going to be 1 minus E. So therefore that actually becomes 1 squared minus E squared. And obviously 1 squared is just 1. So that's 1 minus E to be squared all over 2. Now you can keep it as 1 plus E by 1 minus E, you know. It's all the same. Okay. It'll just help in a few minutes when we're doing the last part of the question anyway. So we need to find, therefore, Q. So we're going to sub P into 1 or 2, whichever you prefer. And therefore I get P, which is 1 minus E squared over 2, plus Q is equal to 1 plus E. So if I multiply both sides across by 2 to get rid of my fraction, then that gives me 2Q is equal to e squared plus 2e plus 1. And then I can divide across there by 2. Now again, you can leave it like that, or you might spot that if I factorize out e squared plus 2e plus 1, factors that multiply to give you 1 and add to give you 2 are e squared plus e plus 1. E is common, 1 is common, and we actually end up with e plus 1 by e plus 1, which is the same as saying 1 plus e squared. And that's all over 2. Okay, so now we have the velocity afterwards, and that was Q, and that was OR. Okay, so let's have a look on the next page then, right? If we line these all up. So by lining them up, we say after the second collision, we now know that P, the first ball, has a velocity of 1 minus e in the I direction, and that was in meters per second. Q now has a velocity after P is collided with Q and Q is collided with OR. It now has a velocity of 1 minus e squared all over 2. That's in the I direction, again meters per second. And OR, after Q is collided with it, now has a velocity of 1 plus e to be squared over 2, and that's meters per second. So we go back. Oh, sorry, that actually, just noticed there that squared is in the wrong place. Sorry now. Squared. But I'm sure you all had the right answer there and wouldn't have that mistake, okay? And then we go back and we can see obviously that was our velocities after each. Okay, so the second part of the question says we have to show there will be at least one more collision, right? So P has collided with Q. Q is now moving off. Q is colliding with OR, and OR is now moving off, right? So if we're looking at Q's collision versus OR's collision, if we look at them, all of them, well, clearly OR has a bigger velocity than Q. So if there's going to be another collision, we would say if there is a third collision, then we would expect that P's velocity has to be greater than Q's velocity. So you'd expect that if P collides with Q, Q takes off, Q collides with OR takes off, Q is going to slow down after colliding with OR, and P is still moving, so you would expect P to be catching up with Q. So of course, what was P's velocity? Well, it's 1 minus E, and greater than Q, well, Q is 1 minus E squared over 2. And therefore, if I multiply both sides across by 2, that gives me 2 minus 2e is greater than 1 minus e squared. If I bring everything to one side, that gives me e squared minus 2e plus 1 is greater than 0. And that's a quadratic. So if I solve this quadratic inequality, so again, I'll just do some rough work over here to the side. So we have e squared minus 2e plus 1. So factors that multiply to give you 1 and add to give you minus 2 must be minus 1 and minus 1. So in other words, minus e plus 1. E factorizing out as the highest common factor. Minus 1 factors out as the highest common factor, leaving me with e minus 1 by e minus 1. In other words, this can be written as e minus 1 to be squared greater than 0. And that's obviously true, because any real number squared is positive. Okay, so therefore, if I'm looking at that, well, what must E be? Like, when will this actually be true? When will the P's velocity be greater than Q's velocity? Well, if I look at these factors over here, that means that E must equal 1, right? So if I actually sketch that as a positive quadratic, because it's a positive coefficient there for E squared, it only touches the x-axis once, it touches it at 1, so it has one repeated root. And of course, we're looking for where is it greater than 0. So of course, greater than 0 is between these two values here. In other words, it has to be less than 1, but E can't be greater than 0, and it can't be greater than 1. Always lies between these two values. So of course, we say that it is true for E less than 1, okay? Because it can't be greater than or equal to 1, because this here is greater than 0. So therefore, that's where is y above the x-axis. So y above the x-axis is all these values here, okay? But of course, E can't be greater than 1. It's not possible. The E can't be less than 0 either. So realistically, we should be saying 0 is less than or equal to E, which is less than 1. So this is what E has to be if there is one more collision. Okay, so in terms of marks, we were 5 marks for this last final statement. We had 5 marks for getting out our second set of velocities. We had 5 marks for getting our 2 simultaneous equations. And we had 5 marks for solving our first set of velocities, and 5 marks for getting those 2 simultaneous equations. So it has to be for both equations there that you're getting your 5 marks for. So that was 5, 10, 15, 20, 25 marks. So if we put at the start, 25 marks for the question. All right.